Hello, Ian here, Victor Kilo 7, India Alpha November. Now, for some time I've been thinking about what it would take to design and build, hopefully, direct sampling SDR QRP transceiver. You don't see very many of them. There are a couple around, but I've not seen a standalone direct sampling transceiver that you could fairly easily build yourself. The ones I've seen seem to be quite complex and difficult to understand and get into. I've looked at the Hermes, and that's a great project. But I find that the details of that quite overwhelming, at least for me. So I had a look at the type of commercial transceivers with direct sampling, and I've got the block diagrams up here from a couple. So I'm looking at the FT710, and that's a great transceiver. And you can see it's got a bandpass filter, RF amplifier, some gain, the ADC, FPGA, and so forth, DSP. And looking at the FTX1, another great transceiver. I was looking at the HF section here, bandpass filter, some gain, ADC, FPGA, DSP. Looking at the IC7300, I couldn't find a nice color rendition of the 7300, another great transceiver. Filter, I assume there'd be some gain in here, I'd be surprised if there isn't. AD converter, FPGA, DSP. So that's great, but what do you notice about all these block diagrams? Well, nothing useful. It's all hidden in the FPGA block, which tells you nothing about the function. It's like saying in a superhet design, here's some diodes and a transformer, and not mentioning the fact that it's actually an RF mixer. It says nothing about function. And so they don't really talk about the actual advantages of direct sampling. Obviously it's going to be simpler, and then they go into all kinds of usability and some stats on sensitivity and dynamic range and so forth. So after building the phasing transceiver and done all the UI and the DSP at 31 kilohertz sample rate with the INQ quadrature inputs, well, that's 90% of the work done. I just need to figure out how to make the ADC signal, how to take the ADC signal and convert that down to 31 kilohertz IQ, and the DSP is pretty much already done. So what I need is a digital down converter, a digital up converter, like the 7300 shows here. That runs at least twice 30 megahertz for the HF portion of the band, so at least 60 megahertz, but also with some margin, and be exactly divisible by 31,250, which is my sample rate for the DSP. So I looked at what ADCs and DACs are available and settled on the AD9236, which is 12 bits. It has a sample rate of 80 megahertz. The DAC, I looked at the AD9740, and that's 10 bits. And the 10 bits should be fine, because if every bit is 6 dB, then you've got at least 60 dB for transmit. That should be fine. And that device easily handles 80 megahertz. But now a bit of a warning. These devices are not cheap. This is not going to be a low-cost project. I think I do know the AD9236 is about $50. It's single quantity. So, okay, settled on 80 megahertz. So we need to take those 80 megahertz, 80 million samples a second, and generate a quadrature signal and decimate to the 31 kilohertz that I need sample rate, IQ samples. So that's a decimation factor of exactly 2,560. So to do that, there really is only one practical option, and that is to use the so-called CIC filter, followed by an FIR filter to finish off with. You need the FIR filter because the CIC is just a moving average filter. It's mathematically exactly the same as a moving average filter. And the filter response of a moving average filter looks like this. Let me just grab this website. I'll link this website in the comment. Or is it here? Here's moving average filter filter shape. But you can see here it is actually 60 dB down at this point. This is a fourth order filter. So we take that CIC and do the we look at the cutoff. So what the filter shape doesn't look great, but what's important is that the cutoff portion allows you to reduce the sample rate sufficiently to allow the FIR filter to take over. So in this case, I want the CIC filter to decimate by 512 and let the FIR filter do the rest. So the FIR filter will see samples at 80 million divided by 512. It'll see samples at about 156 kilohertz. So the FIR calculates at 80 megahertz. So it has 512 cycles to do its thing. So it turns out it can do an FIR tap in one clock cycle. So we could have an FIR with 512 taps or coefficients if we needed it to be that long. So now the CIC filter needs to operate at 80 megahertz. So how's that done? Well, it doesn't take 512 samples, store them, add them up and divide. So this is where the trickery of the CIC comes in, and that's this website takes you through it all. But the end result is, you can see how it works here. This is the end result. And I worked out, so they've actually shown here a third order CIC. I worked out that I need at least a third order CIC, which is just cascading three filters, one after the other, to improve the filter response needed to get the sample rate of 156 kilohertz. So the key trick the CIC uses is the whole filter can be broken up into three adders, that's these three adders, and three subtractors. And only the three adders need to operate at 80 megahertz. So after the three adders, it takes one sample every 512, this is here, and then it does the subtractions. So this is, believe it or not, this is the same as cascading three moving average filters and decimating by 512. That'll be Daisy. Okay, so what about the quadrature and generating the IQ signals? Well, you can build, what you can build is a direct digital synthesizer with a sine and cosine lookup. The DDS is just another adder feeding the lookup index. So the value of the input sample is then multiplied, that is literally mathematically multiplied by each of the cos and sine values to produce the I and Q samples from the input sample. You then of course need 2 sets of CIC and FIR filters for the INQ channels. I've spent a bit of time looking for an FPGA that's easy to use, and after a bit of a search I found this. This is a dev board from Brisbane Silicon here in Queensland. Uses a GoWin device that is actually perfect for this application. It has sufficient logic, it's fast, it has RAM lookups and 8 hardware multipliers that operate at 1 clock cycle, so it's perfect really, not too expensive. I think they're about $20 US in single quantities. They're a great little device, not much bigger than a Pi Pico. So I've started a project on GitHub. I've done most of the Verilog code for the FPGA and some simulations. The good thing about simulating an FPGA is that the final result should work exactly as in the simulation because it's just logic. No analog gotchas in the way. Well, that's the theory anyway. And and on GitHub I put a block diagram of the transceiver and also a summary of the advantages of direct sampling, because you really don't see that very often. And I hope that's interesting. I've also put the Verilog code up there. Take a quick look if you like. Where are we? Okay, so there's the block diagram. It really simplifies things, because what have we got on the receive? We've got the low pass filters, double as the transmit and receive, of an attenuator here for the switchable attenuator here for the receive. Then I've got some high pass filters which combined with the low pass filter form a band pass filter. A bit of gain here, and then the ADC into the FPGA. DSP on the Pico 2. On the transmit side, it does the opposite process of conversion through to 10 bits into the digital analog converter. We have a image reject filter here, the preamp, and then the power amp and the low pass filter. This whole analog section is really simplified. The output of the digital analog converter is already differential, so got put dual filters here into an OPA. I think it's the 2764. Dual MOSFETs here. Really simple analog side here, and the rest is very similar to the phasing transceiver. I'll be using SPI interface to the FPGA. Probably there will be a strobe signal here operating at the 31 kilohertz rate. So all that Pico has to do, the code changes for the Pico compared to the phasing transceiver are pretty minimal, because we take out the audio codec code and replace it with the code to extract the INQ data from the FPGA by monitoring the strobe signal and extracting the IQ data from the SPI interface. I suspect the DSP code can be simplified because some of the code in here is deliberately avoiding the center the DC issues that you get with direct conversion receivers. So I slightly shift the, for SSB and particularly AM, I shift the frequency away from the DC center where you get op-amp, flicker noise and so forth. And I've described some of the issues here. Yeah, zero IF pathologies vanish. Yeah, the LO leakage, the flicker noise, op-amp offsets, and so forth. All that disappears. And so I suspect I can simplify the code in here somewhat and still have as good performance. Anyway, that's all for now. I'll put the links in the description and take it from there. So that's all, and take care. 73 from Victor Kilo 7, India Alpha November.